Okay, so let's start with the next topic. This is functions. First of all, you need to understand what functions are about, what function notation is. So if you have any function that, any equation that's of this type, for example, y equals minus 2x plus 5, there's another way to write this, and that is you say this is f of x equals minus 2x plus 5, right? That's just another way to write down this equation that was in terms of y earlier. You can write that in terms of f of x like this as well. So what does f of x mean? F of x means this thing is a function of x. It's defined in terms of x. You need to understand how to deal with this notation as well. For example, in this notation, when you say input x equals 0, you get y equal to 5 like this. In function notation, the corresponding notation would be that in place of x inside the bracket, you replace 0. That means you're inputting x equal to 0 inside this. And then the result that you get from that, this is the value for y. 5 is the value for y. Similarly, if you want to input x equals minus 3 in this, you have minus 3 in place of inside the bracket here. And the result that you get from that, that's the value for y. That's 11. All right. Now, it could be something other than numbers like this as well. So for example, if you have a function that looks like this, f of x equals 2x squared plus 4x minus 3, and you want to evaluate f of x cubed. What does that mean? Wherever you've got x in this function, what you do is you replace that with x cubed. So let's try doing that. When we replace x with x cubed, this is what we get. Then we simplify that, and the result is going to be the expression for f of x cubed. Okay. Similarly, if you wanted to evaluate f of x minus 1 in this case, all you have to do is just replace x in this function with x minus 1, and then you simplify that, you get the expression for f of x minus 1. Okay, so that's how function notation works. Now, how exactly does a function work? If you have a function that looks like this, f of x equals minus 2x plus 5, what that means is when you input x in this, x is the input that goes into the function, and the function gives you an output. The output that you get, that's what we call f of x, or it can also be represented by y. So how does a function work? You give this function an input. That's normally the value for x. The function applies some operations on that. For example, in this case, the operation the function is applying is that it's multiplying this value by minus 2, and it's adding 5 to that. It's adding 5 to that. These are two operations that the function is applying, and it gives you an output from that. For example, if you input minus 4 in this, minus 2 into minus 4, that will become 8 plus 5, and you would get 13 as the result. Now, the first major thing that we need to know about functions is the concept of domain and range of functions. Okay, I'm sorry. Just give me a second. I forgot to send the link to somebody who just joined. Just give me a second. Just got reminded of that. Okay, so the first major thing that you need to know about functions is domain and range of functions. Okay, now what's the domain of a function? Domain is the set of values of x that a function can take as an input. And what about the range of the function? Range is the set of values of y that you can get as an output from the function. So values of x, they're known as the domain. Values of y, we call them the range. Now about domain, there are only a few things that you need to know about. And that is, for instance, if you have a function that looks like this, f of x equals minus 4x plus 6. Now, does this function have any restriction as far as the values of x that you can input in this is concerned? Is there any restriction? It's a straight line function. You can input any value for x in this, and that will work. For example, you can put a negative value in this, you can put a positive value in this, you can put 0 in this. There's no value for x at which this function is not defined. For a function like this, we often say the domain of the function is all real values. Now, you should be familiar with this notation. If it says something like this, x belongs to R, what that means is x can be any real number, right? So in the straight line, there's no restriction. The value for x can be anything. You can input any value of x in this. There's no restriction. It could be all real values. Compare that with this function. F of x equals 2 into square root of x minus 3. Now, you have a square root function here. In a square root function, inside the square root, you cannot have anything negative, right? So whatever is inside the square root, you want that thing to be positive. So, or it could be 0 as well, but it can't be negative. So x minus 3, that should be greater than or equal to 0. That means that the value for x should be greater than or equal to 3. So the domain of this function will have to be x greater than or equal to 3. Any value that's less than 3 will not work in this function. The function will break because you will end up getting a negative number inside the square root. So that's one thing that you need to know about square root functions, that inside the square root, you can never have something negative. Similarly here, in this function, the part that is inside the square root, that has to be greater than or equal to 0. So what's the corresponding domain that you get from that? X greater than or equal to 7. And the second thing that you need to know about domain is if you have x in the denominator. So if you have minus 3 over 2x minus 8, is this function defined for all possible values of x? Well, pretty much all values, but there's one exception, and that is that the denominator cannot be equal to 0, because division by 0 is not possible. If you end up getting 0 in the denominator of a fraction, that fraction becomes undefined. So how do you get 0 in the denominator here? For 2x minus 8 equal to 0, what's the value of x that you get from that? You get x equals 4. That means that's the value at which this function becomes undefined. So what would you say about the domain of this function? You would say it's all real values. However, there's one exception, that x cannot be equal to 4. So for reciprocal functions in which you have x in the denominator, the denominator's value, that cannot be equal to 0. So whatever is the corresponding value of x that you get from that, that value is not supposed to be equal to 0. Now, these are just two restrictions that you need to know for the domain, that inside the square root, you want something greater than equal to 0. And in the denominator, you want something that is not equal to 0. Apart from this, they will always tell you what the domain of a function is. So these are two things that you may have to figure out yourself. But generally, they will tell you the domain of the function themselves if there is some practical consideration. So these are inherent limitations of these functions, that square root cannot take negative value. You cannot have you cannot have 0 in the denominator. But there's some functions that may not have any inherent limitation in them in terms of their mathematical evaluation. For example, if it's a linear function, there's no problem inputting. You can input any value for x in this. You can put a negative value, you can put a positive value. It can take any value of x and it would still be defined. However, there might be some practical considerations because of which there might be some restriction on x. For example, if x represents price, in that case, price generally cannot be negative. So you would say that the value for x would have to be greater than 0. If there's any consideration like this, they will always tell you the domain of the function in the question themselves. So that's why mostly when you see a question on functions, they will tell you the domain, and what you would have to do generally would be to find the range of that function. Now, that's the major part of this topic, finding the range of different functions. For domain, we only have those two cases, but for the range of functions, we have a number of cases for which we need to, a number of different types of functions for which we need to be able to find the range of the function. Let's start with those different types of functions. First of all, we've got linear functions, straight line functions. Let's suppose we've got a function that looks like this, f of x equals 2x plus 5. And the domain of this function is x greater than or equal to 3. Now, if this is the domain of the function, what's the range of this function? Remember, domain is the values of x, range is the values for y. If it's x greater than or equal to 3, what you can think about is, you can think about the graph of this function. Now, whenever you're thinking about range of functions, for some specific kinds of functions for which you know how the graphs look like, you should always sketch the graph. Linear function and quadratic functions in particular, you should always first sketch the graph, and from the graph, try to think about what the range is going to look like. For example, in this case, 2x plus 5, that's a straight line. It's going to look like this. It's going to be upward sloping line like this from left to right. And now you consider the domain. It's x greater than or equal to 3. Now, what you do is you find the y value at this point. When x is equal to 3, what's the corresponding value for y that you get? You're getting 11 from this. So this is the point that lies on the line. 3, 11, this is the point that lies on this line. And now you think about which part of this graph satisfies this condition. What's the condition? That x is supposed to be greater than or equal to 3. Now, if you have 3 here, which side of this function is going to be valid? The right side. So look at the graph. This is the part of the function that is valid, the yellow part. So what's the range going to be? Range is the values of y that on the vertical axis, how much you can go up and how much you can go down. On the right side here, in the upwards direction, you can say the values of y are always greater than or equal to 11. So that's the range of this function. Now, you might think that it was not really necessary to draw the graph here because we got the value for y, that was 11, and the range turned out to be y greater than or equal to 11. Because this was a greater than sign and this was a greater than sign. So we could just put that greater than sign without drawing the graph. But that's not going to work every single time. Why is that? Because think about this example. F of x equals minus 3x plus 8. Let's say we've got a function that looks like this. In this function, let's say the domain is given to be x greater than or equal to 4. How do you think about the range of this graph now? You input that value of x in this. The value of x is 4. The corresponding value of y that you get is minus 4. Now, what's the range going to be? You might think this is greater than or equal to 4, so the range should be y greater than or equal to minus 4, but that's not correct. And that's something that you understand when you think of the graph of this function. It's a downward sloping line. It's minus 3x plus 8. What does the graph of this function look like? It's going to be going in the downward direction. From left to right, the graph goes in this direction, like this. So what you do is you think about this point. The value for x at this point is 4. What's the corresponding value for y? The corresponding value for y is minus 4. So this is the point that we're talking about. Which part of this function is valid? When x is greater than or equal to 4, which side of the graph? That's the right side of the graph. So from that point, consider the right side of the graph. Look at the yellow part. What's the range of the function? It's going to be below minus 4, less than minus 4. Remember, range tells you about the values of y. Values of y means vertically how far can you go in the upwards direction and how far you can go in the downward direction. So in this case, what's the maximum value of the graph? What's the highest value of the graph? That's negative 4. Lowest value, it can go up to negative infinity. So the range of the graph is going to be y less than or equal to minus 4. That's the range of the graph. You cannot figure that out if you do not think about the graph of this function. So thinking about graphs is really important in problems like these. Take another example. Let's say we've got a function like this. F of x equals minus 5x plus 4. What's the domain of this function? Domain of the function is from minus 2 to 3. Again, you can think of the graph. It's a downward sloping line because the gradient is negative. So it's going to look like this. That's the shape of the graph. It's a downward sloping line like this. From minus 2 to 3, this part of the function is valid. From minus 2 to plus 3. So we have a point on the graph at minus 2, the value for y turns out to be 14. At x equals 3, the value for y turns out to be minus 11. So what part of this function is valid? The part between these 2 points. So on the x-axis now, you are saying any value between minus 2 and 3, that is valid. On the y-axis, any value between minus 11 and 14, that is going to be valid. So what's the range of the graph? The range of the graph is from minus 11 to 14. But now again, you've got to think about the inequality signs as well. Minus 2 has an equal to sign with this. What's the corresponding value for minus 2? That's 14. The corresponding y value for minus 2, that's 14. So on the vertical axis, on the y-axis, the range is also going to have an equal to sign with 14. The domain does not have an equal to sign with 3 there. So the corresponding value for 3, that's minus 11. Minus 11 is not going to have the equal to sign here as well. Okay, so inequality signs, you have to think about them, whether you're going to have an equal to sign or not. You think about the original x value. If that's included, the corresponding y value will also be included. If the original x value is not included, then the corresponding y value would also not be included. Okay. In a linear function, if the domain is all real values, what about the range? The range is also all real values, because horizontally, if the function can go as far as possible on the right side and as far as possible on the left side. Vertically as well, there's no restriction. The graph can go up to positive infinity, and in the downward direction, it can go up to negative infinity, right? So there's no restriction. There's no restriction in the vertical direction as well. You would say the range of this function is all real values. Now that's about linear functions. In linear functions, all we have to think about is the endpoints of the domain. Think about what happens at 3, think about what happens at 4, find the corresponding y value, and look at the graph and see what the range is going to look like based on that. Similarly here, the domain was from -2 to 3. We just looked at the endpoints and we found the corresponding y values, looked at the graph to figure out the range of the corresponding function. Now, the next type of function is when you have reciprocal functions. They're a bit confusing sometimes. These are functions when x is in the denominator. So there's any x in the denominator. This type of function is called a reciprocal function. For example, you could have something like this: 4 over x minus 2 minus 8 over x squared plus 1. We call these reciprocal functions because we've got x in the denominator in these functions. How do you find range of functions like this? Again, you think of those endpoints. However, the graphs of reciprocal functions are a bit confusing. If you know them, you can draw them. However, we can do this without the graph as well. This is one function for which we will not be drawing any graphs ourselves. Sometimes they give the graph in the question themselves. We'll have a look at an example like that. But mostly they will not give you any graph for this. And for this, since the graph is going to be slightly tricky, we would not look at graph. We will do it without that. Now, how exactly is this going to work? Let's say we've got a function like this. For reciprocal functions, if you have any function like this, 3 over 2x plus 1, and you're given the domain of the function that's x greater than 0, we think about the endpoints of the domain. If x is greater than 0, what does that mean? What's the minimum value for x? The minimum value for x is 0. What's the maximum value for x? It's greater than 0. So on the maximum side, it's basically going up to infinity. There's no limit as such. It can go as far as possible. So we consider the endpoints of x. We say, okay, one possible value for x is 0. Another possible value of x is infinity. So what happens when x is 0? What happens when x is infinity? We think about those extreme points. So we input x equal to 0 in this function. X equals 0 gives us 3 as the result. We think about what happens if x becomes infinity. Now, what happens if x becomes infinity? You have infinity in the denominator. Any number divided by infinity, that is going to be extremely small, so it's going to approach 0. If you find that hard to think about, another idea about this could be that in your calculator, just input that function 3 divided by 2 into x plus 1. In place of x, put a very large number and think about what the value looks like. For example, I can input 10 raised to the power 10 in place of x here. The value turns out to be 1.5 into 10 raised to the power minus 10. 10 raised to the power minus 10, that's an extremely small value. So that's basically telling you that that this value is going to be approaching 0. It will be very close to 0, right? So you can think about this from your calculator as well. But just remember, when you have infinity in the denominator, the result is going to be extremely small and it's going to approach 0 eventually. So now the endpoints that we're getting for the y value, they are 3 and 0. So what do we say about the range of this function? We say the range of the function is from 0 to 3, right? So 0 is the minimum value, 3 is the maximum value. Now we're not putting equal to sign with any of them. Why is that? Because in the domain, there was no equal to sign with 0. The corresponding y value for 0 was 3. So we don't put any equal to sign with 3 as well. What about 0? Why are we not putting an equal to sign with this? Because when the denominator is infinity, the value is very close to 0, but it does not become equal to 0. So we don't put an equal to sign with 0 as well. We say the range is just between 0 and 3 like this, and that's our final result. Similarly, if you had an example like this, 1 over x plus 5, you want to find the range of this function. The domain of this function is x greater than 0. Now, again, how do you think about that? It's greater than 0. So what's the endpoints of the domain? The minimum value is 0. The maximum value is infinity again. It can go from 0 to infinity. We think about what happens when x is equal to 0. And we think about what happens when x is going towards infinity. Now, the problem in this function is we cannot really input the value for x as 0 here because that becomes undefined. So how exactly do we think about this? Since it's greater than 0, we can think about a number that's very close to 0. So if you input 1 over 0 in your calculator, that's going to be undefined, right? That will not give you any value. So the workaround for that could be that you input a very small value, 0.000, input a lot of zeros there, and think about what the result that you're getting. That's 10 raised to power 23, or whatever, however many zeros that you have there. Depending on that, you'll get a very large number here. So what that tells you is that when x is when x is close to 0 here, the value of this whole function, that's extremely large. So that goes towards infinity. Or another way to think about this is, just remember, when you have 0 in the denominator, the value becomes very large. Although, strictly speaking, in mathematical terms, we say that this is undefined. However, since this is greater than 0, when you have a very small value, the overall result is going to become very large. So that's actually going to approach infinity. So that is what happens when x goes towards 0, the value for y, that is going to go towards infinity. So that's one endpoint that we've got for the range, that's infinity. Then think about what happens when x goes towards infinity. When x goes towards infinity, when x is a very large number. Now, if x is a very large number, we get something like this: 1 over infinity plus 5. Now, what's 1 over infinity? 1 over an extremely large number, that's going to become 0. But then we're adding 5 to that. So it becomes 5, and that's the result that we've got. So what's the range then? The range is from 5 to infinity. Okay, that's the range that we've got, 5 to infinity. This is one way to write this, that the range is from 5 to infinity. Another way to write this could be that just y is greater than 5, because infinity is not a limit as such. It's just y greater than 5. All right. Okay. Let's have a look at this example. 1 over x minus 3 whole squared. The domain is x is greater than or equal to 5. Domain is x greater than or equal to 5. That's the domain of this function. Again, we think of the endpoints. We think of what happens when x is 5 and what happens when x goes towards infinity, right? These are the endpoints of the domain from 5 to infinity. Now, what happens at 5? We can just input 5 in the function, and that gives us 1 over 4. What happens at infinity? When you have infinity in the denominator like this, again, what happens is the number is going to approach 0. So you get 0 from that. So the endpoints that you're getting for the range here are from 0 to 1 over 4. So that's the range that we write here. Now, do we put an equal to sign with any of those numbers? How do we think about that? It's x greater than or equal to 5. So the corresponding value for 5, 1 over 4, that is going to have an equal to sign here. But when the denominator is infinity, in this case, the value is going to be approximately equal to 0. It's not going to be exactly equal to 0. In that case, we don't put an equal to sign with this case. Okay, all right. Let's move on. So, okay, just a reminder. Question. I'll be taking your questions at the end. Okay, so otherwise it will take too long. It's already going to take too long. Like four and a half hours today. So just a reminder what we discussed yesterday, that while I'm explaining this, I'll be reading some of your questions. If I can incorporate them right there, I will do that. Otherwise, I'll be answering your questions once we're done with the topic. Okay. Otherwise, it will become too slow and we'll not be able to do many topics today. Okay. Okay. All right. Now, the function is defined as follows. So keep a note of your questions. We will be answering them. Okay. All right. The function f is defined as follows. F of x is equal to square root of x minus 1 for x greater than 1. That's a function that we've got. Now, find an expression for f inverse of x. Now, that's fairly straightforward. Now, let's think about this part. It says the diagram shows the graph of y equals g of x, where g of x is equal to this. Now, we've got a graph of this function. This is the reciprocal function. In this case, we think of the graph to state the range of the function. How do you do that? Look at the graph. Remember what the range represents. Range represents what's the maximum value going to be on the y-axis and what the smallest value is going to be on the y-axis. So what's the highest value on the y-axis on this graph? The highest value on the y-axis is 0.5. You can find that by inputting x equal to 0, the y-intercept of the graph. Put x equal to 0 here, that gives you 0.5. So you say the maximum value for y is 0.5. And what about the minimum value? You can see it's becoming an asymptote here on this side and also on this side. So on the lower side, the value is getting very close to 0. You can think about what would happen if x becomes very large here on this side. In the denominator, you would end up getting infinity, and then the value is approaching 0. So what's the maximum value that you're getting on the graph? 0.5. The minimum value, that's 0. So what's the range going to be? It's going to be from 0 to 0.5. We put an equal to sign with 0.5 there because 0.5 is actually part of the graph. But we do not put an equal to sign with 0 there because it's not becoming equal to 0. It's only approaching 0 on the x-axis. Okay? That's what the range of this function is going to be. So for reciprocal functions, if you do not have a graph given, I would not recommend that you draw the graph. It's going to take time and it's a bit complicated. Just think of the endpoints. If you have the domain given, just think of the endpoints. In this case, for example, if x is greater than 0, 0 is one endpoint, infinity is another endpoint. Just check what happens at those points. If you have a graph given, in that case, you think of the graph itself. In that case, think of the graph itself. Think of what the maximum value on the graph is, and think of what the minimum value on the graph is, and that will give you the range of that function. Okay. Now, so in general, when you're finding range of any function, these are the important points that you have to consider. Endpoints of the domain, we've seen them in the previous examples that we've seen in straight line functions as well, and also in the reciprocal functions. We think of the endpoints of the domain. However, there are some functions that have turning points as well. For example, in this reciprocal function that we had, we also had to think of this turning point. Now, for reciprocal functions, they will always give you the graph in case you have to think of the turning point. If they do not give you the graph, then there would not be any turning point, and you can just think of the endpoints. However, there are some functions for which you need to be able to think about the turning points yourself. For example, quadratic functions and trigonometric functions. For these two functions, you will have to consider these two sets of points, endpoints of the domain and the turning points of the function. These are 2 points that you will always have to consider to understand what the range of the function is going to look like. Let's have a look at some examples of quadratic functions now. Let's say we've got a function like this, 2x squared minus 12x plus 24, and the domain is all real values. Now, for a quadratic function, if the domain is all real values, the range is not going to be all real values because the quadratic functions look either U-shaped or N-shaped. So they will have some maximum value or some minimum value. So how do you find range of quadratic functions? You always have to find out the turning point of the quadratic function. We know how to do that, minus p over 2, a differentiation, completing square. You find the turning point using any method. Let's say, in this case, the turning point turns out to be 3 and 6. Now, since x could be any real value, it could be all real values. What that means is, on this graph, you think about it, what's the lowest point on the graph? The lowest point of the graph is 6. On the upper side, there is no limit. The value of y could go up to infinity. So we say the range of this function is y greater than or equal to 6. That's the range of this function. Remember, the range is on your graph, what's the maximum point and what's the highest point and what's the lowest point. That's the range. The lowest point in this case is 6. There's no highest point. So we say the range is y greater than or equal to 6. Now, if they restrict the domain, so if it's the same function, but they restrict the domain like this, they say that x is now less than 5. X is less than 5. Now, what does that mean? How do you think about the range of this function? Now, you have to think of the turning point and you have to think of this point 5 and consider both of them to figure out what the range is going to look like. Find the value for y when x is equal to 5. That turns out to be 14. Mark that point on your graph. Now, this is what the graph is going to look like. It's a U-shaped curve. You mark the turning point. Where is this point going to be? X equals 5 is going to be on the right side of the turning point. That point is 5 and 14. That's this point. Now, which part of the function is valid? X less than 5. That means we're looking at the part that is towards the left side of 5. So all of this part of this graph is valid. Now, in this yellow part, what's the lowest point? The lowest point is 6. What's the highest point? On the left side, you can see the graph is going as far up as possible. It's going up to infinity. So what's the range of the function then? It's y greater than or equal to 6 in this case. Take another example. If we had that same function, but the domain was now x greater than or equal to 4. What about this now? We think of the value for y when x is equal to 4. That turns out to be 8. This is the point on the graph when x is equal to 4. What part of this graph is valid? To the right side of 4. To the right side of 4, this is the part of the graph that is valid. What's the corresponding part on the curve? I've shaded that here. So vertically now, what's the range? The lowest point on the graph is 8. The highest point on the graph is infinity. So the range turns out to be y greater than or equal to 8. So for quadratic functions, you always have to sketch the graph, mark the part of the graph that is valid for the given domain, and in that part, think about what's the lowest value on the graph and what's the highest value on the graph, and that will be the range of the function. Let's consider another example. If it was x less than 0, again, you think of that point when the value for x is 0, the y value turns out to be 24. It's the same turning point because it's the same expression as before. 3, 6. Which side of the turning point is this point going to be? X equal to 0. It's on the left side of the turning point. So we mark that point. Now, which part of this graph is valid? To the left of 0. So what's the range? This is the highlighted part. This is the valid part of the graph. On the graph, think about what's the lowest point. The lowest point on the shaded part and the valid part is 24. The highest point, that's infinity. So the range is going to be greater than 24. We don't put an equal to sign here in this case because the point 0 was not included. So the corresponding value for y, 24, that's also not included. We don't put an equal to sign in this case. Okay. Let's take one last example in this, or the second last example. The domain is x between 0 and 4. Okay, so now one of these points is on the left side of the turning point, 0. The other point is on the right side of the turning point, 4. So this is one point, this is another point. You find the corresponding values of y at both of them. They turn out to be 24 and 8. And think about what part of this graph is valid. So this yellow part is valid between those 2 points, between 0 and 4. This is the part that is valid. Now, what's the range going to be? Look at the graph. Look at what's the lowest point of the graph. The lowest point of the graph is 6. And the highest point of the graph is 24. So what's the range going to be? It's going to be between 6 and 24. Now, since the point 6 is included because that's in the middle of that valid part, 24 is also included. Is that included? No, 24 is not included because the value for x here, 0, that 24 corresponds to, that was not included. So we don't put an equal to sign with 24 here. So that's the range. It's from 6 to 24. That's the range of this function. If you had something like this, if the domain is from -1 to 2, now which part of this function is valid? Again, think of the turning point. The turning point is here. Where are these 2 points going to be? Both of these x coordinates are less than the x coordinate of the turning point. So both of these points will be on the left side. So this is x equals 2. This is x equals -1. The value for x has to be between these 2 points. So now this is the valid part of the graph, the shaded part. What's the range? Think of the lowest point in this region and the highest point in this region. The lowest point in this region is 8 and the highest point in this region is 38. So that's the range of this function. It's from 8 to 38. That's what we write there. We do not include 38 because -1 was not included. So we don't put an equal to sign there. But there was an equal to sign with 2 here, so the corresponding value 8, that does have an equal to sign. Okay, so these are all the different cases that you could have in a quadratic function. You always have to sketch the graph, find the turning point, shade the part of the graph that is valid, and in that shaded part, think of what's the lowest point on the graph and what's the highest point on the graph, and that will give you the range of the function. Next, we've got trigonometric functions. How do you find range of trigonometric functions? Let's say we've got a function like this, y equals f of x equals 3 minus sine x, and the domain is from 0 to 360 degrees. And we want to find the range of this function. Now, whenever a trigonometric function, sine and cos in particular, whenever their cycle is completing, whenever their cycle is completing, so from 0 to 360, sine x completes its one cycle. For sine and cos in particular, their values are between -1 and 1, right? The graph of sine and cos, both of them, their lowest value values are -1, their highest values are +1. They're always between -1 and 1. So whenever they're completing a cycle, if you want to find the range of a function that includes one of these functions, all you have to do is consider the extreme values of sine and cos. So in this case, we've got sine. What are the extreme values of sine? The lowest value of sine could be -1. The maximum value of sine could be +1. So once we input sine x equal to 1 in the function, that gives us one value. And then we input sine x equal to -1 in the function, that gives us another value. And we say the range of the function is going to be from 1 to 5. And that's our final answer. Take another example. Let's say we've got this function. Now this is tan. On tan, that rule does not work. So this function is actually this misprint here. It's 3 minus 2 into tan of half x. That's what the function is. You want to find the range of this function. Now tan does not have its values between -1 and 1. Tan can go from negative infinity to positive infinity. In this case, you just have to check the endpoints, check what happens at 0, check what happens at pi, and that is going to be the range of the function. 0 is giving you 3, pi is giving you negative infinity. So you say the range is going to be from -infinity to 3, or if you say -infinity to 3, that's the same thing as saying that it's just y less than or equal to 3. Now for sine and cos functions, you try 1 and -1. If the cycle is completing, for tan, you just check the endpoints, check what happens at 0, check what happens at pi, and that will give you the result. But if you have sine square or cos square, what about that? Look at this example. So let's say we have a function that looks like this. Y equals 2 sine square x minus 3 cos square x, and the domain is from 0 to pi. Okay, now what about this? Whenever you have a square function, now if you have sine or cos, their values are between -1 and 1. But when you square something, you cannot have a negative value from that. So cos square is going to be between 0 and 1, right? So these negative values are also going to become positive. And so it's the values for cos x are basically between -1 and 1. So these negative values, when you square the function, they also become positive. So now the square function only has values between 0 and 1. So for sine square and cos square, what you would do would be, you would consider 0 and 1 as the endpoints. But for finding range of these functions, first of all, you would have to convert them to the same function. For example, in this original expression, you have both sine square and cos square. In order to find the range of this function, you either want to convert both of them to sine square or both of them to cos square. That's why they make you do that in the first part of this question already. They make you convert the function to cos square first of all. Now, once you have done that, in this expression now, 2 minus 5 cos square, all you have to do is try the extreme possible values of cos square. What were the extreme possible values of cos square? They were 0 and 1. Input 0 once, and then you input 1. The result that you get from that will be the range. You'll say -3 is the minimum value for y, 2 is the maximum possible value for y, and that's the range of this function. This is one way of doing this, although I now actually recommend using your calculator for this as well, and that makes it even easier. And that is basically this idea that you just put this function on your calculator. Just put this function on your calculator. It's the same for sine square, yes. For cos square, sine square, you just input 0 and 1 as the extreme points. But there's another way to do this, and that is the way that we use to sketch functions. Use the table function. This function is in degrees right now. So what we can do is we can select degrees from here. In the table function, input this 3 minus 2 sine x. Now the interval that's given is from 0 to 360. So start at 0, end at 360. And what about the step? I recommend whatever is the interval that's given, you divide that by 8 generally, right? So if this is the interval that's given, 0 to 360, 360 over 8, what does that give you? That gives you 45. Take that as the step, and that will give you enough values to basically understand what the maximum value of the graph is going to be, what the minimum value of graph is going to be. So step 45, just input this on your calculator, and see what you get. This is the function that these are the values that you're getting. Just look at the table and see what the maximum value is and what the minimum value is. In these values, you see 1 is going to be the minimum value. There's no value that's less than 1. And 5 is going to be the maximum y value. And that's what you write there. You write that the range is from 1 to 5. Similarly here, again, you can just input this function in your calculator directly and see what the highest value for y is in the table function and what the lowest value of y is in the table function, and that should work. In this case as well, for the square function, you can just input that directly like this. You would say f of x is equal to 2 sine square x, sine of x whole squared. So in your calculator, you have to write down sine square x in this form, sine square x minus 3 cos square x just input this function on your calculator, and then what's the domain that you're given? It's in radian first of all. We'll have to convert the angle unit. Sorry, let me go back there. That's the table function. 2 into sine of x squared plus, or in fact minus 3 into cos of x whole squared. You could input this form, or you could also input this form. Both of them will work because it's the calculator doing it, so you won't have to worry about this. What's the starting value? It's 0. What's the end value? You're ending at pi. And what's the step going to be? Divide that by 8. Pi over 8, and see what that gives you. Look at whatever is the maximum value in this table. So minus 3 is one value that we're getting. That seems to be the least value. Keep going on. What's the maximum value? The maximum value that we're getting is 2. The maximum value is 2. Minimum is minus 3. Maximum is 2. That's what you write there. That's the range of this function. So you can use the calculator to do it as well. Okay, that will also work. All right. So now sometimes what happens is they give you the range of the function themselves. They give you the range of the function themselves. For example, in this function, they tell you that f of x is equal to a minus b cos x. And they're saying that the maximum value of f of x is 10 and the minimum value is minus 2. Now, how do you think about this? How do you find the values of a and b in this first part? We have to find the values of a and b. Now, for this, as we'll see later, you can think of the graph. That's one idea. That the graph of the cos function, it has its maximum value at 10 and its minimum value is at minus 2. So where is the baseline going to be? The baseline of the graph is going to be exactly in the middle. What's the midpoint of minus 2 and 10? That is 4. That's the midpoint. 4 is the midpoint. Now 4 is the baseline. So the number that's outside here, that represents the baseline, as we'll see in function transformations as well. This represents the baseline, so you can write a equal to 4 there. And then this number b, that represents the amplitude. What's the amplitude going to be? The maximum vertical distance from the baseline, that is 6 units from 4 to 10 or from minus 2 to 4. That's the value of b that you get. You say the value of b is going to be equal to 6. That's one idea. Thinking of the graph, think of the baseline, and think of the amplitude of the graph. The other idea is, this is the function that you've got, a minus b cos x, and you are given the range of the function. Again, it's a cos function. It's completing one full cycle. You input cos x equal to 1 once, and then you input cos x equal to minus 1. Input those two values and see what you get from that. 1 is giving us a minus b. Minus 1 is giving us a plus b. Which of these values is bigger? A plus b, you're adding two numbers up. So a plus b has to be bigger. So we say that is going to be 10. And a minus b is the smaller value. We say that's going to be minus 2 because they told us that the least value of the function is minus 2 and the maximum value of the function is 10. So we say a minus b equals minus 2 and a plus b equals 10. We get two simultaneous equations from that, solve them, and you get the result from that. Now, this is one idea, but thinking of transformations makes it much quicker. So when you have the range given like this, you can think of the graph, think of where the baseline is going to be, think of what the amplitude is going to be, and based on that, you write down the values of those unknowns. Okay, let's resume. All right, so this is the next thing that we need to know about the different types of relations two variables can have with each other. So there are four different types of relations that any two variables can have with each other: one-to-one, many-to-one, one-to-many, and many-to-many. Now, what's a one-to-one relation? One-to-one relation means that for each value of x, we've got only one value for y, and for each value of y, we've got only one value for x. So for every x, we've got for each x, we have only one y. For each y, we've got only one x. What kinds of functions are these? For example, straight line like this. You could have a curve like this. In this curve as well, you have one value for x for every one value of y, and one value for y for each value of x, right? The other type of function is many to one. In these functions, you can have multiple x that can give you the same value for y. For example, in this case, you've got these two values of x that are giving you the same value of y. One very common example of this is quadratic functions. In quadratic functions, for example, if you have y equals x squared, -2 gives you 4, +2 also gives you 4, -1 gives you 1, +1 also gives you 1. These are called many to one relations. All polynomials apart from linear functions, they are generally many to one. Cubic function, for example, if its graph looks like this is a many to one function. Then you have a one to many relation. In one to many relation, you can have multiple y values coming from one single x. So one x can give you many y. That's a one to many relation. For example, you could have a curve that looks like this. This one value of x that's giving you multiple values of y. One value of y here, another value of y here. That's called a one-to-many relation. For example, if you have a function like this, y squared equals x, this is a one-to-many relation. And then you have a many-to-many relation. For example, if you have a circle or an oval, this is a many-to-many relation because one x can give you many y, one y can also give you many x. So on both sides, it's many-to-many. This is a many-to-many relation. For example, this value of x that's giving me this y and also this y, and this value of y that's giving me this x here and this x here. This is called many-to-many. Now, what's important to know in these relations is, I'm sorry. Yeah. So these are four different types of relations: one-to-one, many-to-one, one-to-many, and many-to-many. Only the first two, one-to-one and many-to-one, we classify only these first two as functions. The last two, one-to-many and many-to-many, they are not functions. They are relations, but they are not functions. Only one-to-one and many-to-one relations are functions. So for a relation to be a function, the condition is there should only be one output. So it could be one-to-one or many-to-one. You cannot have multiple outputs. That's not allowed. And out of these functions, only one-to-one functions have inverse. Many-to-one functions do not have inverse, because when you inverse a many-to-one function, that will become one-to-many, and one-to-many is not a function. So for many-to-one functions, the inverse does not exist. Inverse only exists for one-to-one functions. So you need to know about these relations for understanding inverse functions. Now, how do you identify if a function is one-to-one or not? We have this test for this that we call the horizontal line test. And the test basically says, can you draw any horizontal line on the graph of the function that cuts the graph at more than one point? If you can do that, then it's not a one-to-one function. If you cannot draw any horizontal line on the graph that cuts the graph at more than one point, then that would be a one-to-one function. For instance, let's try that here. On this graph, on the straight line graph, if I draw any horizontal line, it can only cut the graph at one point. So this is one-to-one. On this graph as well, if I draw any horizontal line, it can only cut the graph at one point. So this is a one-to-one function. But in this case, in these examples, if I draw a straight line here, a horizontal line here, that's cutting the graph at more than one point. If there's even one line that I can draw like this on the graph, that means it's not one-to-one, because there are multiple values of x that are giving us the same value for y. So this is not one-to-one. Similarly here, I can draw this line and that makes it not one-to-one. So this is the horizontal line test. Can you draw at least one horizontal line that cuts the graph at more than 1 point? If the answer to that is yes, then that's not one-to-one. If the answer to that is no, then it is a one-to-one function. And inverse only exists for one-to-one functions. Okay. So what is an inverse function? You've done this in O levels already for linear functions. How does it work? If you have a function that looks like this, f of x equals minus 2x plus 5. How does the process work? You replace f of x with y first of all, and that becomes x equals f inverse of y like this. Or in fact, I could just know that as well because it's not required right now. Okay, so you could say, let's just say let y equals f of x. So I'll just cut out the detail there. Okay, so this is how the inverse process works. You say let y equals f of x. Then once you do that, it becomes y equals minus 2x plus 5. And now you make x the subject. When you make x the subject, eventually all you have to do is replace x with f inverse of x and replace y with x, and you get your inverse function. Now, what exactly is an inverse function? Inverse function basically does the opposite of what the original function does. So in this original function, for instance, if you were to input x equal to 1, what would you get from that? You'll get y equal to 3 from that. In this inverse function, if you input x equal to 3, you get y equal to 1. So the input becomes output in the inverse function. So it basically does the opposite of this. So going in this direction from 1 to 3, we had to apply f. If we wanted 1 from 3, we apply the inverse function. So x and y, they basically interchange in the inverse function. Okay, so their domain and range also reverses like this. So think about this. If you've got this function, f of x equals minus 2x plus 5, if you input x equals 2 in this, you get 1 from that. In the inverse function, when you input x equals 1, you get 2 out of that, right? So it does the opposite of what the original function does. So when you think about the domain and range of these functions, this is what happens. If the original function f of x has a domain that is x greater than 0, then that becomes the range of the inverse function. That the range of the inverse function that becomes greater than 0. So if this is greater than 0, the range of the inverse is greater than 0. If the range of the if the range of the original function is less than 5, that becomes the domain of the inverse function. So that's the relation between the domain and range of a function and its inverse. The domain of original function becomes the range of inverse. The range of the original function becomes the domain of the inverse. So if the domain is x greater than 0 for the original function, the range for the inverse function would also be greater than 0, but we have to be careful about the variables. When we're talking about domain, it's x. When we talk about range, it's y. So this was x greater than 0 on the left side. For the range, it becomes, for the inverse, it becomes y greater than 0. Similarly here, the range of the original function was y less than 5. The domain of the inverse function becomes x less than 5, because domain are values of x and range is values of y. So if you think about a point, any random point on the original function, if its coordinates are, let's say, a and b, for the inverse function, what happens is the coordinates get interchanged and they become b and a. So x becomes y and y becomes b. The coordinates switch like this. Now, this is shown in graphs as well. When we draw a function, an f of x function and its inverse, when we draw both of these graphs on the same line, on the same graph, what happens is they are always reflections of each other in this line y equals x. If you remember your O-level transformations, when we used to reflect anything in y equals x line, the coordinates used to switch. X used to become y used to become x. That's exactly what happens in a function and its inverse as well. Whenever you draw these functions on a graph, they're always going to be reflections of each other in the line y equals x. So whenever they say draw a function and its inverse and explain or identify the relation between the two graphs, you would always draw this y equals x line as well and show or write that they are reflection of each other in the line y equals x. Now, while you do that, you need to make sure that on both the axes, you're using the same scale. Whatever you have marked as 1 unit on the horizontal axis, you should mark as 1 unit the same distance on the vertical axis as well, because otherwise your transformation, the reflection is not going to look good. And it will not actually look like a reflection if the scale on both axes is not the same. So whenever you draw the inverse function in its original graph, always draw y equals x line and also use the same scale on both axes. Okay, so that we talked about how to find inverse of linear functions. Sometimes you'll have to find inverse of trigonometric function as well. Now that's not very complicated. For example, if you have a function like this, f of x equals 5x, 5 sine x minus 2, what is the inverse going to look like? First of all, we say let y equals f of x. Okay, so that becomes y equals 5 sine x minus 2, make x the subject. Now when you make x the subject, if you have sine x here, when sine goes to the other side, that's going to become sine inverse. So we get x equal to sine inverse of y plus 2 divided by 5. And then at the end, all we have to do is replace x with f inverse, and on the right side, replace the variable y with x, and you get the result from that. Inverse of quadratic functions. Now, quadratic functions also have inverse. Now, how does that make sense? Quadratic functions are generally not one-to-one, and inverse only exists for one-to-one functions. So if you have a graph like this, if you consider this whole graph is not one-to-one because it fails this horizontal line test. But you can still find the inverse if you restrict the domain of this graph. So for example, if you had this quadratic function, x squared minus 2x plus 3, and the domain of this function was x less than 0. Now, the turning point of this graph is actually when x is equal to 1. So where is this point going to be? X equals 0. This point is on the left side of the turning point. So that point is somewhere here. This is the point 0 and 3. So which part of this graph is valid? Only this part, to the left of x equal to 0. Now this yellow part, if you just focus on this part of this function is indeed one-to-one. So for this yellow part, we can find the inverse. Now, how will that process work? How will we find the inverse of this quadratic function? Whenever you have to find inverse of quadratic functions, the first thing you always have to do is complete the square, because otherwise you would not be able to make x the subject. So whenever you have to find inverse of quadratic functions, you always complete the square for that function first of all. So in this case, for instance, when you replace f of x with y initially, then what you have to do is you have to complete the square for that, because then you can make x the subject. When you have completed the square and you got this form, you take the constant to the other side. So you get this thing, x minus 1 whole squared equals y minus 2. And now you take square root on both sides. When you take square root on both sides, do not forget the plus minus, because whenever we take square root, we always have plus minus. But then we have to decide whether to use the plus sign there or the minus sign there. So when we make x the subject, in this case, we're getting 1 plus minus square root of y minus 2. That's the result that we're getting. But that's the expression that is basically the inverse of this whole thing. And that graph, basically, the graph of this thing would look like this. The one that you see at the bottom here, you have one part here, you have another part here. And that's not even a function. This is one to many. So plus is giving you one part and minus is giving you another part. You only have to consider one of them. It can either be plus here or minus here. You always have to first write plus minus there and then figure out whether to use plus there or minus there. Now, how do you do that? Once you've made x the subject, you look at the domain that is given for that question. The domain is x less than 0 in this case. So you say, okay, the domain is x less than 0, and we are getting 1 plus minus square root of y minus 2. How can we get a value of x that is less than 0? Do we get less than 0 value when we do 1 plus something or 1 minus something? We can only get less than 0 when we do 1 minus something. So in this case, we choose the minus sign, and we say the inverse, therefore, is going to be 1 minus square root of x minus 2. So using the domain of the function, when we have made x the subject, we have to decide between the plus and minus in this function, and then just write one of them. Sometimes it's going to be negative, sometimes it's going to be positive. You have to think about it using the domain like this. Consider this example. Let's say we've got this function, x squared minus 2x plus 3. How do you find the inverse of this function? Again, you complete the square first of all, you make x the subject. Eventually, you will get something like this, 1 plus minus something. It's actually the same expression as before, but I've changed the domain now. The domain is from 1 to 6 now. What about the inverse of this? Now the domain is from 1 to 6. How can you get a number from this expression that is between 1 to 6? Would you have to do 1 plus something or 1 minus something? If you do 1 minus something, that value will be less than 1. That's not what we want. We want something that's greater than 1. So the final sign that you use here, it's going to be a plus sign. So the inverse function therefore becomes 1 plus square root of x minus 2, and that's your final result. So always complete the square, and then you make x the subject. Do not forget to put plus minus with the square root there. And then you use the given domain of the function to figure out whether to use plus or minus in your final result. That's how you find inverse of quadratic functions. Let's have a look at a couple of examples in this quickly. Let's say we've got this function, 2x squared minus 8x plus 11. And the first part is just about completing the square range. I just want to focus on this part. First of all, explain why f does not have an inverse. So this function is defined for all real values of x. Why this function does not have an inverse? Because the graph of this function would actually look like this. It's a U-shaped function. It's not one-to-one. So whenever they ask you something like this, whether a function has an inverse or not, you think about whether that function is one-to-one or not. So in this case, this is not one-to-one because it fails the horizontal line test. That means that the inverse does not exist. So that's what you write there. It's not a one-to-one function. But then this last part is important. It says there's another function g of x, and that is 2x squared minus 8x plus 11. It's the same function as before, same expression as before, but the domain has changed. And the domain is that x is less than or equal to some value. Now, we need to state the largest value of a for which this g of x function would have an inverse. Now, what's the graph of this function going to be like? It's a U-shaped graph like this. And they are saying that the domain of this graph is x less than or equal to a. Now, we will have some turning point of this graph. We have already found that in the second part for finding the range, the turning point of this graph is 2 and 3. That's the turning point of this graph. Now, if on the x-axis, you have some point A somewhere, what's the largest value of A that you can have so that this function would have an inverse? It becomes a one-to-one function. If I put A here on this side, then this part of the function would be valid. To the left of A, this is not one-to-one, and that would not work. If I put A on the left side here, then to the left of A, this part of the function would be valid, and this is one-to-one. This could be one possible value for A, but they are asking us for the largest value for A for which it would have an inverse. So how far can A go toward the right side so that it would still have an inverse? So I can start from the left side of this function. I can keep going on. The yellow part still has an inverse. It still has an inverse. I can go up to the turning point. At this point, if I were to go any further, the function would not remain one-to-one. So what's the largest possible value of A that we can have? The largest possible value is when we are at the turning point. So what's the value of x at the turning point? That is 2. It was the domain of the function, right? X less than or equal to A. So we say the largest possible value of A here could actually be 2, and that's the result that we write down there. We say the largest A is therefore 2 because that is when this function would still have an inverse. It will be the x coordinate of the turning point. Similar to that, sometimes they ask you for the smallest value of something for the function to be a one-to-one function, and then the domain has x greater than or equal to something. In the previous case, it was x less than or equal to something. In that case, we were looking for the maximum value. Now it says x is greater than or equal to k. Now, that means in this quadratic function, so you can go through the rest of the parts in your own time later on, but this is the function. and the domain is x less x greater than or equal to k. We want to find the smallest possible value for k for which this function would have an inverse. So again, think of it the same way. It could be at the turning point. If the value for k could was even slightly to the left here, then the function would not be one-to-one anymore. So any such question that like this, where they ask you for the maximum or smallest value of a constant such that the function remains one-to-one, what you do is you think of the turning point. The turning point is going to be that maximum or minimum value, the x coordinate of the turning point. That will be the value that you write there. It's k equal to 3 in this case. Okay, then you have composite functions. Composite functions are when you have one function inside another function. Yeah, and you have one function inside another function. Now, what do they look like? So let's say we've got a function f of x and we have another function g of x. They're both defined for all real values of x. F of x equals 4x minus 3 and g of x equals x squared plus 2. These functions are defined for all real values of x. How do you evaluate the function f g of x? Now, f g of x basically means that you want to input g of x inside the function f. Okay, you want to input g of x inside the function f. So the way to evaluate this is that you introduce an extra bracket here like this, and then you say inside the function f you have to input g. Input g there. The function g is x squared plus 2. And then you're saying f of x squared plus 2. Inside this function, wherever you have x, you just replace that with x squared plus 2, simplify this, and you get the function f g of x. What about g f of x? G f of x would be that inside the function g, you input f of x. Now, what's f? F is 4x minus 3. So you basically say inside the function g, wherever you've got x, you replace that x with 4x minus 3, and that gives you the function gf of x. That's how you evaluate fg or gf. Now, it's important to remember fg and gf are not equal to each other in general. These are not numbers that are multiplying that if you change the order, it would remain the same. These are functions. If you input f inside g, that's a different function. If you input g inside f, that's a different function. They are not equal to each other in general. Then you have this notation, f square of something or g square of something. What does that mean? F square is not the same thing as saying if the function f of x is 4x minus 3, f square of x is not this, that you say 4x minus 3 whole squared. That would be for f of x whole squared. That's a different thing. F of x whole squared, that would be 4x minus 3 whole squared. But when it says f square of x, what that means is you've got the function f coming twice there. So it's a composite function such that you're inputting f inside the function f. Okay, so function f is being put inside itself. So inside f, you're inputting f 4x minus 3. So wherever in that function you've got x, you replace that with 4x minus 3, and you get that result. To simplify that, you get that result. You could have three functions like this sometimes as well. You've got f here, you've got g here. You may have to evaluate f squared g of x. What does that mean? You first of all break it down into parts like this. You say, okay, f squared means f, and then g. And then you put a bracket with the function that is closest to x. What's the function that's closest to x? That's g right now. Input the value for g there. The value for g is x squared plus 2. You input that here. And now you put another bracket to the next function like this. Evaluate f of x squared plus 2. So inside the function f, you input x squared plus 2. That becomes 4 into x squared plus 2 minus 3. Simplify this. When you simplify this, you get something like this. Now, finally, it means you input 4x squared plus 5 inside this expression. So when you have three functions like this, you go step by step like this. You put this bracket, you evaluate this thing, then you put another bracket, you evaluate this thing, and then finally you will get something like this that you can simplify finally. Okay, so you can have three functions like this as well in composite functions. Okay, now sometimes what you end up getting in these problems is, in recent papers you'll find this multiple times. If you have a function f of x equals 4x minus 3 and another function g of x equals x squared plus 2, and you are given that f h of x is equal to g of x, and you want to figure out what the function h of x is in terms of x. So we are given this equation, f h of x is equal to g of x. And what we have to find out is the function h. So we want to make h of x the subject somehow. Now, how can we do that? We want to get rid of f from this side. Now, the way to do that is we apply the function f inverse on the left and also f inverse on the right side of this equation. So we can apply the same operation on both sides. Since we want to get rid of f from there, we say, let's find the f inverse function. First of all, f inverse turns out to be x plus 3 over 4. And now we apply the function f inverse on both sides of the equation in the beginning because f is on this side. So we have an f inverse introduced here because f inverse and f, they're opposite of each other. They will cancel each other's effect. So we will get rid of them on the left side. We're just left with h of x there. On the right side now, we have f inverse of g of x, and that's something that we can evaluate. We know the function f inverse. Inside the function f inverse, all you have to do is input x squared plus 3 in place of x, and you would get that function h of x. Now, in this case, it was fh equal to g. It could also be reversed. So what if we had h f of x equals g of x? What do you do in this case? Again, if you had to find the function h of x from this, you want to get rid of f from this side. How do you do that? How do you get rid of this function f? Now, the function f is coming on the right side here, as in after h. In order to get rid of this, you will have to introduce f inverse on this side now. Rather than in the beginning, you have to introduce f inverse afterwards at this point. So you do the same thing on both sides of the equation. You have an f inverse here, you have an f inverse here. Now on the left side of the equation, these two basically cancel each other's effect, and we're just left with h of x, and that equals g f inverse of x. Inside the function g now, you have to input f inverse, and that gives you the function h of x. So if you want to make one function the subject from an expression like this, whatever function it is that you want to eliminate from that side, you apply the inverse of that function, either in the beginning or at the end, to get rid of that function from there. Okay, now this is an important part of composite functions, and that is, if you have a function f g of x that looks like this, f g of x, how exactly does this function work? This function works like this. Step by step, what happens is the input that you give to the function, that is first going to go to g, the function that's closest to that. So input goes to g first of all. And then g gives you an output. That output is g of x. And then what happens is that output that you get, that goes as an input to the next function, which is f. And from that, you get the final result, which is fg of x. That's how a composite function works. The function that's closest to the input, that's applied first, and then the next function after that. Now, this gives us something very important about the domain and range of composite functions. So you'll have problems like these where they say, you have a function f of x that looks like this. You have another function g of x that looks like this. And you want to figure out if the function f g of x can be formed or not. Now, in this, we consider the function f as the outer function. We consider the function g as the inner function. The function that comes first, we call that the outer function. The first function that is close to x, that comes after, we consider that the inner function. Now, there's a condition for the function f g of x to be formed here. And this is what that condition looks like. So think about this. The function f can take any positive value. The function g, that can take all real values. Now, remember what's going to happen? The input is going to go to function g, and g is going to give you an output, and that output is going to go to the outer function, and that outer function is going to give you the final output. Now, for this to work, the output that you're getting from the function g, the range of function g, since that has to go as an input to the function f, it should be possible to input all possible values from here in the function f, otherwise the function would break. So the range of the function g, it should be compatible with the domain of the function f. Otherwise, we would have a problem. The function f would not be able to take that as an input and the function would break. For instance, in this case, if you find the range of this function g, it's a quadratic function, you can find the range of this. The range of this function turns out to be y less than or equal to 3. So it can give you any value that's less than or equal to 3. So at this step, the function g could give you any output that's less than or equal to 3. But the problem is the function f, that can only take values that are greater than 0. And now we've got a problem because the function g can give any output that is less than or equal to 3. Now, less than or equal to 3 also means that you could have some negative values. When you have a negative value and that goes inside the function f, you would have a problem because the function f cannot accept it and the function would break. So from this, we actually get this result that this function cannot be formed in this particular example because the whole range of the function g, all the possible output values from function g, they cannot be input in the function f, or in other words, the whole range of g is not part of the domain of f. Since it's not part of the domain of f, the function would break, it cannot exist. Now, the summary of all of that is this condition that we've got, and that is a composite function, for example, fg of x, it can only be formed if the whole range of the inner function, in this case, the inner function is g, is part of the domain of the outer function. If this condition is met, then the composite function can be formed. If this condition is not met, then the composite function cannot be formed. The whole range of the inner function, it should be part of the domain of the outer function. You need to memorize this. Range of the inner function, domain of the outer function. They should be compatible, otherwise the function cannot be formed. Inner function is the function that's next to x, outer function is the function that comes first. This condition needs to be met for this condition needs to be met for the function to work, otherwise it will break. And if a function can be formed, in that case, let's say if the function is fg of x. If the function is fg of x, the domain of this function is going to be the same as the domain of the inner function. Domain of the composite function is the same as the domain of the inner function. Why is that? Because remember, in fg of x function, the input was first going into g, right? G was the first function that took an input. So if function g cannot take something as an input, that means the composite function cannot take that as an input. So the domain of the composite function should be the same as the domain of the inner function. This is the summary of all of that. The condition for a composite function to be formed is this: range of the inner function should be part of the domain of the outer function. And if a function can be formed, the domain of the composite function is the same as the domain of the inner function. Let's have a look at this example. Let's say we brought this function f of x equals 2x plus 3, x is greater than or equal to 0, and we have another function g of x that's ax squared plus b, and x is less than or equal to q. Now, in this case, in the first part, they ask us to find the values of a and b. Let's say we've done that, and we found that the composite function is this. The composite function is fg of x equals 6x squared minus 21. Now, the second part says find the greatest possible value for q. Now, what is q? Q is coming in the domain of the function g and the domain of this composite function. Now, what does it mean, find the greatest possible value of q? You've got a composite function here. What's that composite function? The composite function is fg of x. This is the composite function. The inner function in this composite is g. This is the inner function. So g is the inner function and f is the outer function. What's the condition for the composite function to be formed? The condition is that the range of the inner function should be part of the domain of the outer function. What's the domain of the outer function? Domain is x greater than or equal to 0. So this is the function g. This was the inner function. This is the function f. This is the outer function. The domain of the outer function is x greater than or equal to 0. That means the range of the inner function, that should also be y greater than or equal to 0. What's the inner function? It's the function g. So we say this y value, the y value of this function, all of this, it should be greater than or equal to 0, right? This represents the y value. This whole thing is y. So this has to be greater than or equal to 0. So we put that greater than or equal to 0. We solve that inequality like we solve quadratic inequalities, and we get this result from that. X is less than or equal to -2, or x is greater than or equal to 2. Since the question said x is less than or equal to q here, we consider the case that has the less than or equal to sign, and we say the greatest possible value of q that we can have in this case is this number here, which is -2. That's the value of q. That's the greatest possible value of q. That's how we use that rule. This is one way with that we use that rule. Then you may have to find the range of the composite function sometimes as well. So in this case, they give us the value for q, and the value of q now they're saying is -3. We found the greatest possible value for q. Greatest possible value for q was -2, but then they're saying the value of q is -3 now. If the value of q is -3, they are asking us to find the range of the function fg. The range of the function fg. Now, how would you do that? How do you find range of a composite function? Range of a composite function is found just like you find the composite function, or just like you find the range of any function. So since we know that the domain is now x less than or equal to -3, and this is a quadratic function, you find the range of this quadratic function like you find the range of any quadratic function. Think about the turning point. Think about the graph of the function. Highlight the valid part of the graph and see what's the lowest point on the graph and what's the highest point on the graph, and you get your range from that. So finding the range of composite functions is done using the standard way, just like it's done for any function. Then how do you find fg whole inverse? Inverse of the composite function. Inverse of the composite function. Again, that's also done the normal way. If this is the composite function, just think of this whole thing as y, and then make x the subject, and you get the inverse function from that eventually. All right, so that it works the normal way as well. This is another example. So I'm going to skip the other parts. Just look at the last part here. This is the function f of x. F of x is x squared minus 4 divided by x squared plus 4. The domain is x greater than 2. Now, they're saying explain why the composite function ff cannot be formed. How do you think about that? In the function ff, what's the inner function f? What's the outer function f? So that means the range of f should be part of the domain of f. We know the domain of f, that is x greater than 2. In the second part, they make us find the range of the function f as well. It's a reciprocal function. We find the range of the reciprocal function like we normally find the range of any reciprocal function. The range turns out to be 0 to 1. Now, the function f is both inner and outer function. Now, the range of this is from 0 to 1. Domain of this is x greater than 2. Is this whole range part of the domain? It's not. The range is from 0 to 1. That these values cannot be input inside the domain of the same function. That is why you can say this function cannot be formed. Okay. Let's look at one last example. It's been a long session on functions. Let's have a look at this. We have a function f. We have functions f and g. They're defined for all real values of x. We did a very similar example in quadratics on this as well. So let's let's consider that again, just as a reminder. So we have this function f of x. That's a quadratic function, and they say that g of x is another function which is 5x minus 1. Given that the range of the function gf is greater than or equal to 39, find the value for k. Now, how do we think about this? We're given the range of the composite function. We're given the range of the composite function. Now, what's the composite function? You have to find that first of all. How do you find that? Gf of x, you input inside the function g, the function f, simplify everything, and it turns out you end up getting something that looks like this. 5 into 3x minus 2 whole squared plus 5k minus 1. That's the function that you end up getting. Now, they are saying the range of the function is greater than or equal to 39. This is the range of the function, greater than or equal to 39. So what's the range of the function from this? The number that's written outside, that's 5k minus 1. That's the y coordinate of the turning point. What's the y coordinate of the turning point going to be? This is the y coordinate, right? 5k minus 1. In the standard form, y equals a into x minus h whole square plus k. So the range of this function would be greater than or equal to 5k minus 1. So that means 5k minus 1, that corresponds to 39. So 5k minus 1 equals 39. And that gives you the value for k, that is 39. So if they give you the range of a function themselves and there's something that is unknown, what you can do is you can find the range of the function yourself in terms of that unknown variable, and then you compare both of them and you get the value of that unknown from that. All right. The next part is something that we already discussed. You can have a look at this. That's it on functions. I hope that was helpful, although we ended up taking a lot of time and even though I was trying to be very quick as well. I hope that it made some sense. If you have any questions, you can let me know. And now we can have your questions quickly. Okay, so some of you seem to have problems understanding the standard methods for some of these questions. For that, you need to make sure that you understand the detailed method. Again, the point of the session is revising what you already know. If you do not understand something at all, then you have to make sure that you go through a detailed video for that. So, for example, reciprocal functions, how to find range of those functions. You can, what I'll do is I'll add to the group description the P1 playlist. You can watch that particular video, range of reciprocal functions from that, to understand how that works. Because going into a lot of detail right now, unfortunately, is not going to be possible because there's so much that we still have to cover, and we will be otherwise, pulling an all-nighter. Then you guys already will get tired by 9 p.m. I think you're already tired at this point from the messages that I'm seeing. It seems like that. So if we start going into too much detail, that'll be very difficult. Okay, so that's one question that I can quickly answer about x equals 0. Where's that? Reciprocal functions. Okay, so some of you got confused here. Okay, so in this case, for instance, when you have domain x greater than 0, you cannot input x equal to 0 in this function directly. If you try doing that under calculator, that will give you an error. One way to think about this is you say, okay, 1 over 0, just remember that's going to be an extremely large value. So you can think of that as infinity. So infinity plus 5 is still infinity. So that's going to give you infinity. Or another way to think about this is, since you cannot input 0 as such, think of a very small value instead. It's x greater than 0, right? Greater than 0 means any value that's greater than 0. So you want to check what happens at 0, try a value that's very close to 0, like 0.0000, and then put many zeros there, just to understand what it is going to look like. Now, 1 over an extremely small number like this, what do you think is going to happen? The overall result is going to be very big. Now, in that result, even if you add 5, that does not change much. It's still infinity. So that's what you get. You get infinity in this case. So that's one extreme value that you're getting for y. The other extreme value that you're getting is 5. So you say the range is between 5 and infinity, or in other words, it's just greater than 5. That's the range here. Okay. Graph of reciprocal functions, you would not have to do that. You can do everything without sketching graphs yourself. If you need the graph, for example, if the graph has a turning point, in that case, this method would not work. In that case, they will always give you the graph themselves, like in this example. There are only, I think, 2 questions like this in recent papers in which you have a turning point on the reciprocal function, and both of them, they give you the graph themselves. You won't have to draw the graph of a reciprocal function yourself. That's not something that's required in your syllabus. Okay. Any other quick questions? Okay, let me go back there. So this is clear now, the 5 to infinity one? Okay, so when we write this 5 to infinity, both of these are acceptable. Both of these are acceptable. So 5 to infinity means the value has to be greater than 5 and up to infinity. Now, infinity is not a number as such, so that's not a limit. So you can also write that as y greater than 5. Both of these are acceptable according to the marking schemes. So you can write any of them. You can say y greater than 5 or y is between 5 and infinity. Both are fine. Okay, so in this case, we're saying it's 1 over x minus 3 whole squared. So it might have a turning point. No, it's not a quadratic function. It's quadratic in the denominator. These functions still do not always have turning points as such. Uh, Even if they have it, the domain that they would give, the domain that they would give, it would always not include that turning point. So we won't have to worry about the graph. Okay. So in reciprocal functions, when they do not give you a graph themselves, it always means it's going to be a one-to-one function. That means it's not going to have any turning points. So you don't have to worry about the turning points in that case. Okay. If there is a turning point, they will always give you the graph themselves. So that's not going to be a problem for you guys to figure out.